thank you for the organizer to allow me to participate in this workshop that has been very stimulating. It is in the context of a longer program that is called Foundation of Data Science, and it would be nice maybe for us to have a discussion of what data science really means. One idea that has helped me think through it quite a bit in the last few months or so is this notion that data science should be an intelligent and trustworthy data analysis in a world where we collect data first, and a lot of it, and then ask questions later. And there's many things that are reflected in this order of data collection. For example, the difficulty of doing causality statements, because most of the data that is collected first is going to be observational. There is also implicit the fact that very often we learn from the data what questions to ask. And so there is a whole branch of adaptive data analysis that poses a lot of theoretical interesting questions that this audience might want to address. I want to focus on a very specific version of that and give you an example in which sense we can learn which questions to ask from the data and some of the challenges that we encounter and contributions that we have in this direction. So I work with biomedical data, and in biomedical data, data acquisition is still costly, so we don't have gigantic sample sizes as in other fields. The way we have experienced the big data revolution is that we have high throughput measurements, so we measure very many variables. And very often modern scientific investigations start by testing a large collection of hypotheses that are somewhat loosely formulated. They are not derived by prior evidence, but they are really trying to collect every possible relationship between the variables that we measure. While we do testing, this is really an exploratory endeavor in the sense that the rejections are not going to result in providing one drug or not to a patient, but they are really used as a way of identifying hypotheses that are warrant follow-up. Still, because we do so many tests, it is meaningful to correct some measure of global error. It's okay to follow up some false leads, but you don't want the majority of the things that you follow up to be false. So a criteria for global error that fits the bill of in this context is the false discovery rate, which I'll remind you is the expected value of the proportion of false discovery over the total number of discoveries. And I have rewritten it here explicitly this way to emphasize that there's two averaging going on here. One, we do the expected value over all the possible realizations, so we don't give a guarantee on the false discovery proportion on these particular data sets, but only on average over all the possible data sets that we might have collected. But also we don't give guarantees on specific rejections, but only on the average of these rejections. So what is the thing I want to point your attention to is in many settings like this, it's often the case that the rejections that we obtain are not a final product. What do I mean is that they do not represent scientifically distinct discoveries. So in order to articulate a meaningful message in the paper or in the grant that you write for follow-up or whatnot, some filtering is in order. Let me give you a couple of examples. This is a picture from an fMRI study of schizophrenia and a 2D rendering of it. In these cases, you do a test for each voxel, and voxels are these little cubes where you do measurements, and now we only see squares, and you get an answer for each voxel saying, yes, there is an association between activity at this voxel and the trait that you are looking at. So you get an answer for each of these little squares. I don't know if you can pick up the squares here, but voxels don't have any biological meaning. So when you have answers like this, you think, well, there is something going on here. I don't really care that there are 50 or 30 little squares that colored up here. They're just pointing out to one particular region. So if you want to describe your discoveries, you might describe saying, oh, I have these, 9 areas where I've seen some activation. This is the same setting in an area where I work a lot, which is genome-wide association study. It's simpler. Instead of being in 3D, it's just 1D. We have on the x-axis the genome, and you test for association between a genetic polymorphism, many genetic polymorphisms, about 1 million of them, and a phenotype of interest. And what you have in this plot are minus log 10 the p-value, so some sense of the strength of association that you detect, and each dot corresponds to a different genetic polymorphism. And what you can see is that when you see association, it typically shows up not just at one SNP, at one of these polymorphisms, but at many of them. Now, when you're going to report the findings, you're not going to report every single one of these SNPs saying, oh, I have found an association between SNP 1, 2, 3, and 4, and in this case, this is glaucoma. But you're going to report an association between glaucoma and this particular locus. Here you cannot make out the names, but the scientists here have identified different genes that are in these different loci. Often, if you cannot identify the gene, what you report is simply the SNP that has the smallest p-value, and you use it as an indicator of that particular locus. This is a more complicated for me to describe examples, but an interesting one, and it refers to a new type of studies that it's becoming popular, that is called FIWAS. So you test for association between one exposure, or in this case, one particular HLA haplotype, and every possible disease under the sun. How could you possibly do that? You rely on cohorts of individuals that you have, for example, all the patients of an hospital, or all the people that are taken care by a health maintenance organization as Kaiser Permanente, or all the insurance claims that a particular insurance has. So you imagine that on these people you can measure the exposure or the genotype here and see if you can see association between this exposure and any of the diseases. And how do you represent any of the diseases? In this type of data, the diseases are represented using what we call ICD code, so this International Classification of Diseases, that has a tree structure. And for example, if we look down here, this node here, it incorporates all the diseases of the eye and neighboring areas, and then you get more specific to different neighboring areas. So for example, here you have the cornea and something else, and then you say which type of diseases of the various areas. So this is glaucoma, and then you have different type of glaucomas. The colors in these plots indicate the strength of the detected association. So darker green means that you have seen a stronger association, and white that you have seen no association at all. So let's look at the top here. You see lots of these nodes are associated. Now, if you are able to squint there, you see that these ones are all kind of spondylitis, which is an inflammation of the spine. And you really don't want to report that you have association with spondylitis A, spondylitis B, spondylitis 3, and maybe a generic spondylitis. There is only one type of association that you have seen, so you want to collapse somewhat, summarize your results. Okay, so what I'm going to do next is to show you a few cartoon examples to convince you that some of the rules that we may use to summarize and filter down these results have impact on FDR control, and then introduce you to a method that we have developed that keeps FDR control when we focus on selected discoveries. Now, while all the mistakes and blunders are mine, this is work that I did in collaboration with Jean Katsevich and Marina Bogomolov. Marina Bogomolov is on the faculty at the Technion, and I have worked with her for a few years and learned a tremendous amount about FDR controlling procedures from her. And Jean Katsevich is a graduating student at Stanford with whom I had the privilege to work. He is also here today, so I also have the privilege to defer to him any technical questions that you might have. So here is my cartoon version of the brain. So let's say that each square here represents an hypothesis that we want to test. And we are going to identify the non-null hypothesis with an asterisk. So those ones are the discovery we might want to make. And now let's say that we do testing and we have an FDR controlling procedure at the 10%, and my rejection set is represented by the square that I colored in pink. So if you are quick at counting, you'll see that you have 48 pink squares, so 48 discoveries. 5 of those are false, And so your realized FDP, it's really quite close to the 10% target. Now, if this is our brain study, we really don't want to report all of these 48 discoveries as distinct. So what we might do, we might identify clumps of adjacent discoveries and say, well, I'm going to report with more weight one of them and the other one downweight them a little bit so that I really have one separate discovery for each clump without forgetting the other ones. And the way I put down weights here is that you have a value of 21 for total weight discoveries, 4 weight of false discoveries, so your false discovery proportion gets up to 19%. Say that you select only one of those discoveries from each clump, okay? So you look at the clumps and then you select one representative discovery. This is what's happened here. Now you have 12 filtered discoveries and 4 of those are false. So your false discovery proportion now it's up to 30%, okay? So I haven't changed my testing. I simply have filtered down my set of discoveries to really come up with distinct one that makes sense reporting. Let's look at a problem that looks a little bit more like the ICD code setup. So here my hypotheses are on a tree, and parents' hypotheses are equal to the intersection of the children hypothesis. And in my coding, a true null hypothesis is represented by a circle and a false null is represented by a square. So suppose I do some testing and I indicate with the rejections with a red border. Say these are my rejections. I now have a realized false discovery proportion of 3/14. Now there is some redundancy here, right? Because if I have discovered H4, H5, H6, and H7, of course I have discovered H16. It's just the intersection of those. I don't need to report all of these findings. So what has been proposed even back in 2008 by Dani Yekutieli and other colleagues is to say when you have a setting like this, what you should report are the outer nodes. So the discoveries that are not parent to any other discoveries. The outer nodes of the discoveries in this graph are the nodes shaded in blue. So say that I do that, my false discovery proportion, which was already pretty high in this example, raises now to 3/9. Okay, so I hope I have convinced you that while the adagio, it's true that if something is true, it says so no matter how you slice it. When you allow some noise to contaminate your discoveries, how you slice this discovery does matter. And I'm not just wanting to play on language, emphasizing that when something is true, you can do this. It's also relevant to understand that if we use as a target error rate something like family-wise error rate, we have no problems, okay? Because we're guaranteeing ourselves that the probability with which we make even one false discovery is very small, so we can regroup our finding in any way we like and we'll still be fine. But when we use a more lenient criteria like the false discovery rate, which is really a statement on the average of the discoveries that I make, how I count these discoveries matter and how I slice them matters. Now, this problem had been noted before, and in fact, if you look at the literature for FDR control in MRIs and functional MRIs, there's some beautiful work that proposed specific solution there. It had been noted before in the context of genome scans, and my colleague David Sigmund and Nancy Zheng and so on have contributions there. We don't have really solutions for the problem of controlling false discovery rate on outer node yet. But what we want to do is to look at this problem at the general level and propose a general purpose procedure that allow us to have FDR guarantees on the finding that we'll actually report. So to do that, let's take a step back and look at the problem in somewhat abstract fashion. Now this is as matzy an audience as I ever get to address, so I'm sure this will not be problematic for you, but there's a little bit of notation in the next slide, so bear with me for a little bit. So we start having our M hypothesis. And what we want to do is to say, okay, maybe we do testing, but testing is not the end of the story. Then we are going to filter our rejections. Maybe we're going to associate different weights to them. So let's formalize this using this notion of a prioritization vector. So you have for each hypothesis a value uj that it's a number between 0 and 1. That represents what you're going to do with this hypothesis. It's 0 if you're going to forget about it, you think it's not interesting at all, and it can be a number that tells you how much money you're going to invest in following it up, how much space you're going to give it in the paper. In standard multiple testing, this number corresponds to 0 or 1, 0 if you do not reject the hypothesis, 1 if you reject it. And what we are saying is that if you want to incorporate all type of reprioritization that people do on the hypothesis, it is useful to have a continuum value. If we look at the outer node filtering, what are these u's? Are simply you get a u equal, the u's are only 0 and 1, and you are going to be 1 if you are rejected and if you are in the outer node set of the rejections. To give you an example of u that it's not actually 0 or 1, you can think about weighting multiple testing, and Benjamin and Hochberg, for example, in 1997 have introduced a procedure that does FDR control in a weighting setting. So there you have for each hypothesis, prior to do any testing, you have a weight that represents how important for you that hypothesis is, how costly it would be to make a wrong choice with respect to that particular hypothesis. And in that context, our u's are equal to the weight that you decide a priori and then multiply by the indicator that tells you if that hypothesis is in the rejection set or not. We're using this capital U because generally speaking, our u's are a random variable whose outcome will be determined using on the data. Okay, so if u's are incorporating all what we are going to do about this hypothesis, our global error that we should target, whose control we should target, should be defined in terms of these u's. So we have this generalized FDP, which is just like the usual FDP. If instead of looking at u's here, you put an R indicator that tells you is rejected or not. But what we have at the denominator is the total weighted amount of discoveries, and that at the numerator, the proportion, the fraction of the total weighted amount of discovery that pertains to nulls. There are many ways in which one could come up with these prioritization rules. What we're going to focus on are prioritization rules that are defined by filtering rejections. So we're going to look at a setting where we have some multiple comparison procedure, gives us some rejection set, and then we filter these rejection sets. So let me tell you precisely what I mean with filter. So filter is a function that takes as input a rejection set and the data, or really what we do is p-values, and then outputs for you a prioritization vector. So for each of the hypotheses, you have these values u, and what we require is that u is 0 if uj is 0 if the jth hypothesis is not in the rejection set. So what this is saying is that you take a rejection set and you concentrate on a subset of it, or you weight it a bit differently. And we have seen two types of filters. The clumping filter is what I described for you roughly for the brain type data. So you identify clusters of neighboring rejections, and then you select one representative from this cluster of neighboring rejections. Typically, you might pick the one that has the smallest p-value. And the outer node filter, I hope I managed to explain to you what that is. Okay, so what is the goal that we want to pursue? Well, so suppose we have a multiple testing procedure M that gives us some rejection set and a filter F. So this filter and multiple comparison procedure give us this prioritization vector. What we want, it's a procedure that guarantees that the expected value of this generalized FDP on this prioritization vector is controlled. And we call this object false filter discovery rate, and since I'm sure I'll say filter for FDR because it's easier to say, but okay, what we're looking is the FDR on this final set of rejections. How are we going to develop a procedure that does that? Well, we are going to modify ever so slightly the Beniamini-Hochberg procedure. So let me restate for you what the Beniamini-Hochberg procedure does so that it's easy for me to see where we modified, okay? One way of saying what Beniamini-Hochberg does is saying we have a set of p-values and then we consider a series of possible rejection sets indexed by a value t that is the threshold on the p-value that you might consider. So this rejection set t is a set of hypotheses whose p-value is smaller than equal than t. For each of these possible rejection sets, we estimate the false discovery proportion. How do we do that? Well, the false discovery proportion is the number of discovery at the denominator and at the numerator the number of false discoveries, which we don't know, so we need to estimate. And this is the estimate we had in the Beniamini-Hochberg procedure. So lo and behold, for every t, I have an FDP estimate. And what my procedure tells me to do is to look for the maximum value, the maximum t, such that the estimated FDP is lower than my level Q. And then I'm going to output as rejections the rejection set associated to that t star. So what we need to do is to work on this estimate of the false discovery proportion, because this estimate of the false discovery proportion is corresponding to my initial rejection set. Okay, I want it to be an estimate of the false discovery proportion in my final outcome. Okay, I don't want it to be an estimate of the FDP on R, but of this generalized FDP. So what do let's look at it a little bit more in detail. The denominator is simply the count of the number of rejections, and at the numerator I have an estimate of the number of nulls done, a bound of this estimate done assuming that all the hypotheses are null and my p-values are well behaved and so on. I need to change the denominator, okay, because I'm going to change if you remember what happens when I do my cartoons, I change the total count of rejections and it diminishes. So that's what I need to do. I need to modify the denominator to incorporate this different way of counting. I could also change the numerator because in fact I count differently also at the numerator, but that's more difficult and it's really a matter of power. It's not a matter of controlling the FDR. So we don't do that right away. So this is the procedure that we do when we change the denominator of the FDP. Instead of having the total number of rejections in the intermediate rejection set, I simply plug in the sum of my U values. So this gives me exactly the same procedure, a procedure that looks exactly like BH, so that's why we call it focus BH. And we call it focus because instead of it gives a guarantee on the focused set of discovery, we focus on this particular way of looking at what is important according to the filter. To give you a sense of what this does, let me tell you what it's equivalent to in a simpler setting. Suppose you had M hypotheses and you say, oh, I'm not going to test them all. I'm going to only focus on the 100 hypotheses that has the smallest p-values. Then say that you want to have FDR control on the rejections that you have. You cannot apply BH to this 100 hypotheses as level Q, right? Because you already started selecting your hypotheses as those ones that have the smallest p-value. You surely think that you have to pay some price for this selection, right? Otherwise, I always play this game. I say, oh, I want to focus on the one hypothesis that has the smallest p-value, and now my alpha level is just alpha. I don't have to pay any price. So you must pay some price, and it turns out that the price you have to pay is that you can work on this set of only 100 hypotheses, but what you need to do is to do BH on this set with a target that it's 0.05, it's 0.05 is the target you have in mind, times 100 over M. So you pay a penalty for how selective you have been in your initial pass. Now, the focus BH, if you apply it to a setting like this and you work out what does this mean in terms of filter, gives you exactly this procedure. Okay, so when does it work? To state one of the results that we have, I have to tell you what is a monotonic prioritization rule. Well, it's yet another definition, but it's a very simple concept. Suppose you have two sets of p-values and you can compare them so that in one set each p-value is smaller than in the other one. A monotonic prioritization rule tells you that when you have smaller p-value, you have more overall discoveries. So if your filter is such that your prioritization rule is monotonic and the p-values you have are PRDS, then we can prove that focus BH controls the false filter discovery rate at the level that we want. Okay? Now, a cute thing is that outer nodes induce a monotonic prioritization rule on trees. So with this result, we can control we now have a provable procedure that control the false discovery rate on outer node, and this is a contribution to the literature because there wasn't any really known procedure that did that. In fact, the procedure I described for you does a little bit more. Not only we control the FDR on the filtered set, but we also control the FDR in the intermediate rejections. So if I think about the GWAS example, this tells me that I control the FDR of the different loci that I identify, but I'm also allowed to go and look at all the SNP that pass the initial threshold and consider this larger, more fine-grained description of where the association is. And now if we relax the hypothesis on the p-values, so if we assume that the p-values are independent or block independent, so if we make stronger assumption on the p-value, assuming that they are independent or block independent, then we can relax the hypothesis on the filter, and we can also deal with filters that are not monotonic. Last time I spoke here, I got a question about what is PRDS, so I have these details here. If anybody asks me the question, we'll go back to that. So I told you we don't modify the numerator, but the fact that we do not modify the numerator tells us that my estimate that I have is conservative, and it's conservative for two reasons. As every BH procedure, it assumes that it's a bound under the hypothesis that every null hypothesis is true. And also, it doesn't account for the filtering. So if I'm filtering my rejections, I'm certainly diminishing the number of rejections, but I might as well diminish the number of false rejections, and we don't account for that either. Now, accounting for the first one is easy. We can do a story-like procedure and estimate the number of non-nulls, and we can prove that this works if the p-values are independent, which is typically what you can prove for story-like procedure. Accounting for the filtering is more complicated, and we don't quite know how to do it. The only way we have outlined is to use some permutations, and this is a slide that I don't expect you to read. We don't have results that say that permutation really give us theoretical control of the FDR. It's very difficult to have any results on FDR control based on permutation, but in our simulations this works quite well. So there is room for improving power a little bit, and permutation seems to be a viable one. So let me show you a couple of simulations to give you a sense of what's going on. So the first one, it's a setup where we have hypotheses as node in a tree, and in this setup the leaf nodes here correspond each to one gene, and we say that an hypothesis is non-null if this gene is differentially expressed between cases and controls. And the data that we're going to generate has 100 cases and 100 controls. And each parent node is the intersection of the children nodes. So in the setup here, we've decided that these 4 genes are truly differentially expressed, and all the ancestors of these 4 leaf nodes are then non-nulls because we have this intersection description of the parent's hypothesis. The simulation I'm going to show you has 500 replicates for 11 different levels of signal strengths. And how do we get p-value for each node? So we have a simple p-value at the leaf nodes, and every other node has a p-value that it's obtained doing sums of the p-values relative to the genes that are descendant of that node. Okay? So for this one, I do sums of these 2 p-values. For this one, I do sums of these 4 p-values. So what I'm going to do is to compare the performance of focus BH with other procedures, and I want to compare in terms of error rate and power. So let me tell you which procedures I am going to look at and what are their advertised error rate controls. So we're going to consider two procedures that target the FDR on the pre-filtering steps, and then we're going to see what happens if I take the rejections of this procedure and apply a filter. So these two procedures are BH or story BH. Then I'm going to consider a procedure that actually controls the family-wise error rate. Now, any procedure that controls the family-wise error rate controls the FDR, both in the pre-filtering and the after-filtering step. That's a nice property of family-wise error rate. It might seem arbitrary, though, to compare to a family-wise error rate controlling procedure because that's a much more stringent error rate. This particular one has been developed for hypotheses that are on a tree structure and capitalizes on the logical relationship between hypotheses. So whenever you reject one hypothesis, you are going to add to the rejection set all the parents, all the ancestors of this hypothesis. So it is actually a fairly powerful procedure as far as family-wise error rate procedures go. And then we consider two procedures that have, at least in mind, the idea of controlling this filtered false discovery rate. One is the other one is a procedure put forward by Dani Yekutieli. In fact, this procedure can provably control the FDR only when the p-values are independent, which is typically fairly uninteresting in this tree type of hypothesis. And it's a bound, and the bound has a fairly conservative procedure. We are going to use something that Dani Yekutieli found in simulation works, even if it is not exactly the bound that he has in his theoretical results. So we are using it in the most liberal version that seems to have control FDR. Okay, so these ones are the procedure, and I'm going to look at the false discovery rate in the pre-filtered set and the post-filter set, and I'm also going to look at power. And what do I mean with power? Well, when I do this filtering, we have to agree on what power would mean in this context, and what we're going to say is that power is just the ratio between the sum of the UJs relative to true false nulls over the maximum value that this sum could have. Okay, so the power cannot necessarily be all the originally non-null hypothesis, because some of these one might get filtered out anyway when I do my filtering, so that's why we have this Tmax business here. Okay, so there's lots of lines here, but let me walk you through this plot. So we have FDR in the top panels and power in the bottom panels, and on this side we have pre-filter, and on this side post-filter. So the red lines correspond to procedure that target the pre-filter FDR, and in fact they do control it, but you can see that they lose control after filtering. So indeed, if you simply apply BH and then do filtering, you don't have a control, your final results really don't have the reproducibility guarantee that you might want to advertise them with. The structured Holmes is the dark blue line, and indeed it controls FDR in both cases. And the focus BH corresponds to this set of middle blue lines here, and you can see that they all control the FDR, pre-filtering and post-filtering. Now let's look at what happens in terms of power. So these red procedures have the highest power, though it's false advertising because they don't have FDR control in the post-filtering set. So of course, if you make more discoveries, you make more discoveries point. It's interesting to see what happens to the power of Yekutieli and structured Holmes, for example. So Yekutieli procedure even if technically the conditions for his theorems are not satisfied here, does control the FDR, pre and post filtering. It has the worst power. So it is not really a very competitive procedure, besides the fact that it doesn't have necessarily theoretical guarantees. What happened to structured Holmes? You can see the structured Holmes, it's quite powerful here in the pre-filtering set. In fact, its power is very close to the powers of the focus BH procedure. So that seems a little bit counterintuitive. Structured Holm, it's controlling family-wise error rate. We are controlling FDR. We end up having the same power. What kind of a joke is that? That is due to the fact that, as I told you, the structured Holmes enriches the rejection set by including all the ancestors of any rejections. Once you reduce redundancy in your rejections and you do the filter, then this extra addition of rejections doesn't play the same trick. So you can see that now in the post-filtered set, the focus BH procedures have higher power than structured Holmes. Now, what are all these different focus BH procedures? They are the one that I have described for you, vanilla one, original. They are the one that's modified to do something like story, and permutation one. But they all behave the same here, so let's not look too much at this plot, except for seeing that the permutation one, for which we have no theoretical results, does seem to control the false discovery rate. Another example, let me not go through the details of how the simulation was done. Let me just tell you that it's a mock version of a GWAS, so that we generate data so that it looks like data from SNPs, and we are testing for association with one particular phenotype. And because we don't have this tree structure, it doesn't make sense to include in our comparisons the Yekutieli procedure or the structured Holmes, so the plot here is a little bit simpler. What we can see is that if we do not do anything about the filtering step, we are going to lose FDR control quite dramatically. So this is what happens if you do BH plus filter. And let's look now at this true two filtered BH proposal. This is the original one that I have described, and this one, the dashed one, is the permutation. There is also a third line here that has this very light blue. That's what's called here oracle, to say that it's not an existing procedure. Yes?
Chiara, what is the filter here that you're using?
The filter here is the clumping filter. So I identify SNPs that are neighbors, and I select from all the SNPs that are neighbors one representative, which is the SNP with the smallest p-value. So this oracle business, it's not a procedure, it's a theoretical constructions. If you knew how things were, this is the best thing you could possibly do. What is interesting to see here is the permutation one does seem to control the false discovery rate, and it goes quite close to this maximum possible power that we could obtain. Okay, in case you like this so much and you want to do many filters at the same time, we can put together many different filters and give you FDR control simultaneously on all of these filters. So let me conclude. Because FDR is a guarantee on the average of your discoveries, it's really tied up to how you count discoveries. And in order to be valid, any procedure really has to account of all the selection steps that you put into defining what are you going to present in your paper or in your follow-up grant as the discoveries of your study. Now, when this curation process of what are you going to consider really as a relevant discovery can be specified in advance, and this is often the case because in the setting where we work, people use algorithms. You know, it's not that they are going to look at the discoveries and on the basis of their feeling pick one or the other. There are so many of them, they just have to specify we are going to filter them according to this rule or this other rule. So whenever you can specify in advance the rule that you're going to use to reprioritize your discovery, you can incorporate it in the multiple comparison procedures and get the right FDR guarantees I haven't really talked about it too much, and partly because we haven't done too much with it. But in this process, we have also, in trying to be general and defining what is the goal that we had in mind, we have introduced this idea that you can give an answer about an hypothesis that is not binary, 0 or 1, but it's continuous, and the value of that continuous answer can be entirely driven by the data. So you could, you don't have to specify a priori the weight of an hypothesis, but you can use the data to decide what is the appropriate weight to give to that. And I think there is potential to do interesting things there. And I also have not talked about this, but I did emphasize that we have a nice result on controlled outer nodes on trees. A lot of hypotheses that people are interested in testing are not quite on trees, but in directly acyclic graph that don't have only the tree structure. And we've made some contribution to that literature as well. Eugene Katsevich is going to give a lightning talk this afternoon, so if you are shy and asking him questions now, you can ask him this afternoon. He's going to talk about another project that he has done, also related to FDR, and he's going to show some progress on understanding in which sense FDR controlling procedures are maybe more robust than we give them credit for. And that's all. Thank you very much for your attention.
Have time for questions.
So if you had a priori information on signaling pathways, could you embed that in this process in a way that you're kind of looking along the possible genes in which the SNPs would be hitting within those signaling pathways?
Yes, I mean what I've talked about is how you massage or how you interpret p-values that you already have. If you are thinking of, if I have information on the structure, can I do tests differently that it's not incorporated in here? What is also true that even if you don't incorporate the information in how you calculate the p-values, you can do testing strategies that are hierarchical, for example, so that you don't test all hypotheses at the same time, but you say, well, I start over here and I only test children of hypotheses that look promising. And that's also an area in which we have some work. It's not really covered from what I've talked about now. Now, you can also use your definition of filter, you can use it to reflect some of this information. So you could say, maybe my filters are pathway aware. So I'm going to say that any discovery in a certain pathway is somewhat redundant to other discoveries there, so you could implement it in that sense. Elizabeth.
I actually had a question about the hierarchical. Are these even comparable? Like the question of doing like a hierarchical filtering or a screening filter, for example, you have other data, maybe you run an F-test to do the most interesting spots, or you do certain regions and then you try to zoom in, sort of this kind of strategy. Are they even comparable with this framework that you've set up here, or are they just completely...
Well,
like, does it even make sense to compare them, like the methods on the same simulations or something like this? Do they?
So the setup we looked at is where you actually test every hypothesis, and then you have these rejections that can be redundant. If you do a testing that is hierarchical and says, I'm only going to test this hypothesis first and then go down and test only if I reject this one, okay? Then typically there you are you are implicitly going to forget about this hypothesis once you move down. You're automatically looking at outer nodes. So they are comparable in that sense. But when you do the testing hierarchically like that, typically you don't have this problem of having to reduce redundancy at the end. They are compatible in the sense that while I've used Sims p-value to do the p-values from for these ancestors, I could use whatever test I want here. So to test this hypothesis, I could use an F-test or whatever more sophisticated test I have to capture the signal at that level. Now, I say you can. I'm not sure that you have PRDS necessarily once you have this complicated test, simply because PRDS is a complicated thing to verify. But we have done simulations in setup where we don't have PRDS, and nothing wrong seems to happen. It's a fairly robust setting. It's a scientific question. Do you want to do it testing hierarchically versus you test everything? I like hierarchical testing. I think if you can think through, my bend will be to try to do it that way. It is true that in many applications, people don't want to think through very much. And so that's what I mean where you learn from the data which question to ask. You start with this list of all possible hypotheses I could possibly test, and just afterwards you say, well, let me put some order in them.
Yes, maybe I missed this. Is weighted BH a special case of this filtered BH?
Actually not. It is a good question. If we have a setup, we can do weighted hypothesis testing with this filter BH. But the rule that you will get is not exactly the rule that you would get doing a weighted BH as it's described, for example, in Benjamin-Hochberg 97, which is the closer one to us. And I think we are a bit less powerful because since we are treating these weights as if they could be learned from the data, we don't manage to recuperate all the power that it's. Since our V hat is conservative, it doesn't take into account the reduction of the number of discoveries the number of false discovery that it's also induced by filter. I think we are a little bit more conservative than what BH97 would do in this case. But so yes, you can do weighted testing in this framework. If your weights are defined as a priori, I think you're better off using one of the other procedures.
All right, let's thank the speaker again.